in order to now link together orbital motion and gravity, we're going to consider a thought experiment that Newton carried out. We're going to refer to it as Newton's cannon, sometimes referred to as Newton's cannonball. Basically, we're going to consider a cannon on top of a tall mountain. So we're simplifying this and making it an easier situation to deal with. So in order to sort of explain this as we go, I'll just draw a diagram on the left here. And so here's our Earth with a tall mountain at the top of it, and on top of that is going to be positioned our cannon. And obviously a cannon fires cannonballs. And so the cannon is actually going to fire cannonballs faster and faster. And if you think about what happens with cannonballs, they will obviously, once they've been fired, they're going to fall towards the Earth. However, because the cannonball, because the Earth has a spherical shape, they'll actually end up travelling further and further around the Earth. So if we think about a cannonball that's been fired very slowly, so initially it might just sort of drop down into this position just below the below the mountain itself, fire it a little bit more quickly, and it might actually be able to reach further around, fire it faster again, and you see that the cannonball can actually start to end up, say, reaching the opposite side of the Earth. Now we could continue that with any sort of speed up to a particular speed, and we could see what would happen with the motion of the cannonballs moving further around the Earth. But if they're fired at a fast enough speed, what we will see is that the cannonball will be able to travel all the way around the Earth. So the idea there is that as the cannonball's falling towards the Earth itself is actually sort of falling away. It's probably the easiest way to explain it. And as a result, that cannonball, as it travels around, it's continuing to change its path, falling down towards the Earth, but the surface of the Earth is likewise falling away from the cannonball, and so that cannonball continues to move all the way around the Earth and ends up sort of hitting the cannon. In this scenario, we can consider that the cannonball is then in orbit. So it's travelled all the way around the Earth and arrived back at its original place, and if we were able to move the cannon out of the way, then the cannonball would continue that orbit and continue to move around the Earth's surface. If we now link these two ideas, so if we think about that situation, since the cannonball is moving in a circular path, we know that centripetal force must be acting on it. And as we know for centripetal force, the direction of that force is directed towards the center of the motion. Or another way to put it, the centripetal force is perpendicular to the velocity. And if we have this situation, we know then that the cannonball, as it's moving, and that centripetal force is then going to be provided by gravitational force. And we have two equations that we can link together there. We know what centripetal force can be calculated by, and we also know what gravitational force can be calculated by. So we're basically now looking at the fact that we've got a centripetal force. I'll use this subscript C to indicate centripetal force. That's going to be provided by the gravitational force, so subscript with a G here. Now we know centripetal force is given by mv squared on r, and we know gravitational force is given by G multiplied by capital M, so that would be the mass of the Earth, multiplied by lowercase m being the mass of the cannonball, divided by r squared. You can see there there's a few terms that we can cancel, so the mass of the cannonball ends up cancelling, so the mass of the cannonball itself actually doesn't matter. And we've got an r in the denominator on the left hand side and r squared on the right, so we can cancel the r from the left and the squared from the right, so we're then left with v squared being equal to g m on r, or the orbital speed being equal to the square root of g m on r. So that basically means then that the orbital speed of an object, so we were talking here about a cannonball, but we don't have to refer to a cannonball now, we can refer to any object. So the orbital speed of that object at a given radius from the centre of mass, and that would be the value of r, depends only on the mass of the object being orbited. So that we could then look at say the speed with which the moon orbits the Earth, and we could figure out what the distance there would need to be, or we could figure out what the mass of the Earth is. We could look at how long it takes the Earth to revolve around the Sun and the speed with which it travels around the Sun, and therefore we could figure out what the mass of the Sun is. So there's a lot of astrophysics that relies upon this sort of idea of figuring out the masses of objects that are being orbited. There are a few other concepts that tie into this idea of orbital motion. We'll have a look at Kepler's laws of motion in class. They're not specifically covered by this unit, but there's a couple of interesting things you can do mathematically to show some relationships that Kepler discovered well before Newton came on the scene. So we'll have a look at some of those ideas in class.